All right, so moving right along. Up here, you've got one more time the formal definition of Rolle's theorem. And now we're going to talk about mean value theorem. So if you remember, we did extreme value theorem together in class. Now we've gone over Rolle's theorem, and now we're going to talk about the last big theorem that we've got, mean value theorem. So mean value theorem. Mean, the word mean. Mean means average. We're talking about averages. And you can abbreviate this mean value theorem. I think that's a pretty clear abbreviation for this. So it says, if f of x is continuous on some closed interval a comma b and is differentiable on some open interval a comma b. Those are the only conditions to check now for mean value theorem. Then mean value theorem says there must exist a value c on this open interval a comma b where f prime of c, the derivative at that point, is equal to the mean, the average rate of change of the whole interval. F of a minus f of b all over a minus b. We're talking about a value where the derivative, the instantaneous rate of change, is equal to the average rate of change. So let's start using this. We have this function h of x, it's a rational function, and we have a picture of the graph, and we want to know if the mean value theorem applies. We're going to have to say why or why not. So we're always going to go ahead and look at those conditions first. So we have a specific interval that we're focusing on from -1 to 5. And the first condition says it has to be continuous on the whole interval, but this tells us that we have an asymptote at x equals to 0. So no, we cannot use the mean value theorem. So no, mean value theorem does not apply on this particular interval because not g, h of x has a discontinuity at x equals to 0. So that interval is no good. But then we might change the interval and just talk about from x equals 1 to x equals to 5. So does it apply? Why or why not? Well, this is different. On this interval, it's definitely continuous and it's definitely differentiable. We're just really talking about this portion of the graph here. So in this case, yes, mean value theorem applies because h of x is continuous on the closed interval and is differentiable on the open interval. Now, thinking graphically, we want to know what does the mean value theorem guarantee for the function on the interval, and we're going to see if we can do a little bit of drawing to help us with this. Well, like we were saying up here, mean value theorem says that the instantaneous rate of change at a particular point is equal to the average rate of change over a closed interval. So here, the mean value theorem says there has to be, it's guarantees that between x equals 1 and x equals 5, there is some value, we'll call it c, where the instantaneous rate of change, also known as h prime of c, equals to the average rate of change, also known as h of 1 minus h of 5, 1 minus 5. It's that specific interval. So we're saying here, based on the graph, here's the value, or the point, 1 comma negative 2, 1 comma h of 1, 5 comma h of 5. This is the average rate of change. We're saying that there's some point, I don't know where it is, but here might be the point C, where they've got parallel slopes, essentially. The average rate of change is equal to the instantaneous rate of change. So let's use the mean value theorem to find the values of C on this interval 1 to 5. We already checked the conditions, so since we checked the conditions, we can go ahead and use it. We know that h of x is equal to 3 minus 5 x to the negative 1. And we can find the derivative of that using nothing more than power rule, 5x to the negative 2. And the mean value theorem says that h prime of x, this is the instantaneous rate of change, is going to be equal to the average rate. So we should find the average rate of change. We should figure out what h of 1 minus h of 5 over 1 minus 5 is equal to. From the graph, you can see that h of 1 is equal to negative 2, h of 5 is equal to positive 2, and this is going to be negative 4. When we do all this out, we're going to find that this is equal to 1. So now we can set these equal to each other. We're trying to find some value for c. h prime of c is equal to 5c to the negative 2. So 5, and I'm just going to go ahead and use that negative exponent like so, equals to 1. We'll find that c squared is equal to 5. So c is equal to plus or minus radical 5. But we consider the domain that we are using, and that's only from positive 1 to positive 5. So we'll find that c is equal to radical 5 only.